properties. The usual questions we ask is, how can a structure be achieved through processing? Or how can a microstructure be achieved through processing? Or how does a process affect the performance? Or how do you design a structure to obtain certain properties? So these are some standard questions in material science. Typically, it's been done through experiments and computational models, but in recent times, data is playing a larger role because of modern machine learning techniques. So I want to talk about variational autoencoders, which is one of the modern machine learning techniques for use in material science applications. This is a picture of a process design. So this is a work we did for NSF a few years back, designing magnetostrictive materials. The idea is to design a process, and by process I mean deformation process, which could be rolling, it can be drawing, so forging, etc. So these are processes, extrusion, etc. So these are processes that deform the material. Let's say you want to create a turbine blade, you'll have to deform the material. But at the same time, at every point, you're also controlling the microstructure. And the microstructure changes due to deformation. The kind of changes you get in the microstructure are, for example, crystal orientations changes. Every grain in a metallic microstructure has a crystal orientation that if you deform, they're going to change. That's called texture evolution. You can have things like twin variants that emerge. So all of these contribute to evolution of properties in the macroscopic material. So the inverse problem is this. So can you design a process that optimizes the microstructure? And that's the idea behind this talk. How do you design processes to achieve certain microstructures? I know there are people of different backgrounds here, so I want to give a quick introduction to texture. Texture is a difficult concept to explain, but it's basically, think of it as a volume fraction of grains of different orientations. So if you can plot, if you take an EBSD image of a aircraft part, EBSD image gives you grains on the surface. So these are the crystals on the surface, metallic crystals, and each crystal is colored according to its orientation. So you can think of plotting along the x-axis, the orientation, the y-axis being the volume fraction of these different colors, and that gives you an orientation distribution function. Just the difficulty is the x-axis is not a single value, it's the orientation space. So we plot it in the orientation space. So this is just that histogram plotted directly on the orientation space. And this orientation space is for hexagonally closed packed materials. So every crystal has a symmetry, so the space looks different. Now the question is, how do you parameterize the x-axis? In this case, we use a Rodrigues representation, which is angle axis representation to parameterize the space of different crystal orientations. For FCC, the orientation space looks different due to the symmetries. It looks like this. It's a cube with the edges trimmed. And you can, the way we define the ODF is because it's a continuous space, we define the histogram on these nodal points. So we make a finite element mesh of the orientation space. And then at each node point, we can describe the volume fractions. For example, if you want to see how much is the volume fraction of the yellow color in this microstructure, we look for the orientation in this domain. So it could be one of the nodes here. And then we can take that volume fraction, smooth it onto this node. So that's how the orientation is defined. So now the question is, how do you achieve optimal microstructures? How do you optimize this texture from conventional processing? So you need to do process modeling. So you need to identify how a process affects the microstructure. Two ways to do it. One is crystal plasticity finite element, which is a full-scale analysis. We take the microstructure, we define the entire microstructure in 3D using a finite element mesh, and then we can do a compression process. So this, for example, shows a compression process. This is a full field model, so it defines strains in each grain, and the strain can vary within each grain. Computationally very intensive. We have a code, Prism's plasticity code. It's on GitHub that we are developing through a Department of Energy program. It's a massively parallel code developed by a group for doing this. For this talk, I'm going to develop databases which are extremely large. For that, we develop a reduced order model. So in this case, we use an ODF finite element model. In an ODF finite element model, we directly we directly do the deformation process in the orientation space. I'm going to tell you how to do this. We assume all the grains are the same strain. It's a Taylor model. It's computationally cheap. It gives you upper bound stresses, and it tells you how the orientations change in the orientation. So this is the histogram plot I was talking about. The color denotes the volume fractions of different grains. Every point is an orientation. Evolution of orientations is done using a continuity equation. It's very simple. The idea is identical to fluid flow. So you think of a fluid flowing in the orientation space. It follows a continuity equation. Just that the continuity equation is defined in a angle axis coordinate system. So you have a Rodrigues space with its own Riemannian metric. So when you define gradients, just be sure you use the gradients as defined in the Rodrigues space. But it's basically a continuity equation. You can think of orientations changing as you deform, and the orientation move from, if a crystal orientation changes, then the volume fractions move from one point in the Rodrigues space to another point through this continuity equation. So this equation is solved using finite element method. How do you define these velocities? So you define the velocities using a constitutive model, in this case, a single crystal deformation model. Standard crystal plasticity, if you're used to crystal plasticity, I can define this very quickly. You have these 5 laws associated with the reorientation velocity, which I need to compute the texture. So that's an elastic plastic decomposition, a stress strain law, a plastic flow rule, which depends on the slip systems, yield surface, or a shearing rate, dependence on the rate of the rate on the stresses and the slip resistance, and finally hardening laws, which gives you the hardening for the stress strain curve. So these are nonlinear set of equations for predicting strain and stresses, which are solved in example is Prism's plasticity code, which solves this couple set of nonlinear equations. At the end of the day, we just want this reorientation velocity. So we compute this reorientation velocity, and then we pass it to the continuity equation to compute the texture. How do you model different processes? The way we do it is we decompose the velocity gradient into different modes, tension, compression. You have shear modes, rotation modes. By combining these modes, you get a majority of deformation processes, major modes in the deformation process. For example, we can do drawing process using tension or rolling using plane strain compression. And we have developed 6 different processes that we can apply to develop a database. Here is a sequence of processes that we can apply. For example, take an initial random texture, take the material, compress it, put it under tension, roll it, so we can subject the microstructure to different processes. And then we build a database consisting of these deformation modes. So we put these deformation modes, what's the rate of deformation, etc., in a sequence. Typically, if you want to make a turbine blade, you need 21 different processing steps. The GE uses to make turbine blades, 20 plus processing steps. So you can think of these as each stage of the processing step that the texture is being simulated. You can also make a database like this. So you can put it under tension, do one process, but at the same time fork it, do a different process, start from tension Y, do a rolling, then compression. So what we have done here is a database that contains 342,000 process paths. So we do the continuity equation with these processes, with all permutations of these 6 processes, and forking it from different points. So it's a graph structure of how a material changes, the microstructure changes as a function of different processes. So there's a very large database, so we can do some machine learning to understand the process property structure relationship that I was talking about. So the problem statement is this: given the process, physical simulations can give us the ODF. So that's the continuity equation I defined. The inverse of this is not deterministic. That is, given a desired ODF, what is the optimum processing route that gives rise to this orientation distribution, starting from initially random distribution. So starting from initial random distribution, going back, what is the processing route that gives you the property that you need, or ODF, that is a texture that you need. So we propose to solve this inverse problem. It's not easy to solve this because it's a combinatorial problem. These are particularly hard to solve. So we want to solve this using statistical learning procedure. So question is, given a texture, given the ODF, what is the number of stages, what's the processing sequence, amount of deformation each stage. I want to give you some idea of past work. We've been working on this problem for a while. So this is 2009, very more than 10 years back. The field is very fast developing, so the models available are getting better and better. So this was just k-means clustering, just to understand how this database is distributed. So if you take this k-means code, take this 344,000 ODFs, and then start to define classes. They all look like this. So these are 10 different classes that I plotted, or 25 different clusters. If you expand it, they look like this. So if you want to define a process sequence, you look for a similar ODF in the database, and then you can backtrack all the processes that give rise to this particular ODF. The issue with this approach, although you can find all the process stages that lead to a particular ODF, it's not a generative method. What that means is this kind of technique can only predict from among the input ODF in the database. So if your solution is there in the database, you get an answer. Solution is not there in the database, you don't get the answer, because it only predicts what's the closest, and you just need to know if you want to exactly make that microstructure, you don't know what the number of stages should be. Here's another work. This was 2007 in ACTA. So we first developed this PCA representation for texture. So PCA itself is an autoencoder. So the PCA is called principal component analysis. It's an autoencoder. So before I talk about PCA, I want to talk about autoencoders. What are autoencoders? You can take a high dimensional input. This is a neural network. Think of taking a high dimensional input and develop a neural network architecture that shrinks. The number of layers start to shrink. You only have 3 variables here at the center, and then you expand it back. And the outcome of this neural network is the same as the input. So input is same as the output, but your neural network has a bottleneck, and the bottleneck gives you what is called a latent space. So this is a low dimensional representation of the input microstructure. So if your input microstructure is an image of a microstructure, which is 1000 by 1000 that you get from eBSD, then if you run through this encoder, you can reduce that to a 3-dimensional space that you can visualize. If you have thousands of these eBSD images, you can reduce the entire set to a 3-dimensional space that you can visualize. That's called an autoencoder. Autoencoders are useful for these latent representations. So you have a X, Y, and Z that you can plot along an axis, X-axis, Y, and Z axis, and then you plot this latent points. Every point corresponds to a microstructure or an ODF. You can click on a point, see what the ODF is. It's very easy to visualize. You can measure properties of each of these points, draw a property closure. You can identify processes at each point. So this is the cool way to reduce the database complexity. I want to show principal component analysis because we've been doing this in the past. In this case, what you do is this is a simple example of PCA, principal component analysis. It is an autoencoder. I want to show that it is an autoencoder because all we are doing is if you have a set of points A, B, C, D, E, these are the initial points in 2-dimensional space, we find a coordinate system, a new coordinate system, which is called the encoded dimension or a latent space, where you can represent all these points with minimal error, which means we're trying to reduce this error and projection along this line. This problem turns out to be an eigenvalue problem, where you can think of it as a neural network autoencoder with one layer, a linear layer. The linear layer multiplies the input with the eigenvectors of the covariance matrix of data points. And then you get this low dimensional layer, and then you do another linear decoder, and then you get back this. So if you do P transpose with eigenvalues, they are normalized, you get this. The way I think of it is neural networks gives you PCA as one of the solutions because there's no normalization constraint on the eigenvectors. But PCA is one solution for a neural network, but it will give you lots of other solutions that will encode this data. I wanted to show this, the eigenvectors from PCA, how they look like. So although I talked about eigenvectors, they're really eigenbases in the orientation space if you do this on the ODF. So here are 3 different ODFs. They end up being the eigenbasis functions for a tension process. I also wanted to point out this is texture. Anand Kanjarala, who is the host, has I saw a paper of his. He has done PCA for 2-point correlation functions. So you can think of doing this reduced order encoding for 2-point correlation functions also, where you can get a compact space for higher order microstructural descriptors. In this case, I was showing just the orientation distribution space, where you can take this expansion, you can take these coefficients, and then you can plot these coefficients. In this case, if you have 3 basis functions, you end up having 3 coefficients. You plot this latent space, and then you can plot all the textures, pick any point, pick any combination of these coefficients, do a linear summation with the basis, you get the ODF. The issue is not every point gives you a valid ODF. So it's a truncated space mainly because of the normalization constraint. Because the ODF sum to 1, it's a constraint space. You can also think of plotting properties in this space. So that's called a property closure. So property closure is basically a plot of all the properties that you can get from a latent space. So it looks like this for a tension process, where its Taylor factor is plotted along rolling direction, transverse direction. Using the property closure, we can identify how to go from a random texture to any point within this process. So if you want to generate a microstructure that looks like this, I can tell you how much strain, what should be the tension process to lead to this particular ODF. Some cool features about PCA latent space. The latent space is always a plane. We called it a process plane because it's a plane because it's a very simple equation. This is a linear equation, so it's always a plane. It's the equation of a plane. And then you can also cut the space with properties. So if you know a property, that's also a property plane if you use upper bound relationships. So you can identify isolines on this plane. You can take cross sections. These cross sections correspond to ODFs with similar properties. And if you want 2 different properties, you can cross these isolines, find the intersection point, and then define what the ODF is at that point, which gives you that property. Think of this as doing process sequence design also, because I can drop these Taylor factor property closures on top of each other, one for tension, one for rolling, one for tension followed by rolling, etc. So all these closures lie on top of each other. So if you want to go from a random texture, go to a different texture, I can go directly using tension. I can follow the process property closure for a rolling process, reach this point, go to another process, and then go to another process, get back to this different microstructure. So you can go through variety of process sequences to reach from one point to another. Why is this limited? The limitation is, as you can see from here, we need a basis for every process. That's not possible because there are an infinite number of processes. If you think of a 100-step sequence, you have to generate a basis for that. So how many basis sets will you generate? That is a limitation. The dimensionality is also expected to be very large if you want to include all of them in a single basis where you can plot it. So that was the limitation so far. So then I can go to variational autoencoders. So variational autoencoders, first paper on variational autoencoders, which is a very famous paper, came in 2014. The field has, last 6-7 years, the field has exploded. Lots of papers on these generative networks, these so-called generative networks. The other one is GANs. Some of you are using these deep learning techniques. So this was a very recent paper, December 2020. We started doing variational autoencoders to reduce the space to a much smaller complexity. So what are variational autoencoders? Why is it different from PCA or other autoencoders? The idea is this: if you just use a regular autoencoder, you take a circle, square, and a triangle, you run it through encoder, it puts it on a line. That's your reduced space. It's a one-dimensional space. If you take a point sample from this space, you may not get a circle, triangle, or a square. You're getting something like this. Without regularization of this space, you're not going to get similar ODFs. If you think of this as ODFs, I want to interpolate across the space so I can generate new ODFs that are not there in the database, something different from what k-means does. Now we can generate new ODFs which you don't even train with, so you're generating new data structures or data sets from your limited experimental values or computational values. This is variational autoencoder. What it does is it takes a simple autoencoder, think of it as PCA, which takes an input does this eigenvalue decomposition, gets a latent representation, decodes it, gets back the input. A variational autoencoder will take the input, encode it onto a latent distribution, which is a probability, which is very important because it doesn't give you a unique point in the latent space. It gives you a spread of points, which is a continuous spread, and then you can sample from this continuous spread to reach a input reconstruction. The only issue with variational autoencoders, how do you train this? Use backpropagation to train it, because there is a sampling step involved, which is stochastic, so that you can't define gradients to train a neural network. So variational autoencoders use Gaussian distribution. So there are some features that lets you train it. I'll come to that, but before that, how do you generate this latent space? You generate using a loss function, which you can easily understand through a visualization I'm going to show next. So a neural network encoder finds the mean and the standard deviation of this distribution, and then you sample it and do a decoder. The loss function is you want to make sure your output is same as the input, as well as you want to make sure there is a distribution as close as possible to the origin with a small variance, with a variance of 1. If you just use the reconstruction loss like PCA does or an encoder does, you get something like this. The issue with this is if you take a point in the empty part, you don't get anything out of it. You get rubbish ODFs that don't make sense. But if you just use scale divergence, everything groups onto the origin because it's going to be a Gaussian distribution centered at the origin. But if you combine these two losses, what we are really doing is making it a continuous space, as well as discriminating between different ODFs. So in this case, we have some overlap where we can interpolate. And then we have all the ODFs in the database falling in place within a certain region. So we can do some generative ODFs from this space. So what does this do? So if I talked about these triangles and circles, if you make a variational autoencoder, it will overlap these spaces. So going from a circle to a triangle, you can go through intermediate steps like this, but each of these steps can correspond to a valid ODF. So it is a natural transition from one process to another that I was talking about. So what's the structure for our neural network? What we do is we take in the ODF, we run through an encoder space, encoder neural network. We find the mean and standard deviation. We do the sampling. I talked about this issue with sampling, but with reparameterization trick in Gaussians, there is a trick that if you want to generate samples from a mean and a standard deviation, all you need to do is sample from get a random sample from another normal distribution centered at the origin, and then do a linear addition, h times psi plus g, where h is the covariance. H is the square root of the covariance, g is the mean, and then you can do this reparameterization trick so you can fully back propagate, and the sampling is separate from the neural network. This is something that branches off. It's not related to the encoder and decoder variables. So this helps us do the variational autoencoding. And so now the question is, what is the dimensionality of the latent space? Whether we should the ODF space be one-dimensional, two-dimensional, three-dimensional? If you do PCA, then you plot the eigenvalues, it ends up being a very high dimensional space. So idea is to reduce it to 3D at least, so we can visualize the database. Here is an example of how we do it. So we generate different neural networks, each one having different level of latent spaces, and we look at the reconstruction errors. We can plot the reconstruction errors as a function of the inputs. And you see that if your latent space dimension is 1, then you have a larger standard deviation. We get more errors in the output, the decoder. But if you can increase the latent space dimension, you get smaller and smaller, in a sense that we can identify what is the latent space for ODF. For this, the entire database of 342,000 ODFs ends up being a latent space of 3, which is optimal. So we can use this 3-dimensional space to plot entire set of ODFs. If you go to 4, it doesn't give you any additional benefit. Another example is what happens if you, what happens if you do a 2-dimensional space? Then you cannot capture some of the input features. So if these were the input ODFs, these are the output ODFs from the decoder. You want them to be as close as possible within a reasonable loss, which is plotted here. So if you use a 1-dimensional space, although it gives you a reasonable reconstruction, it just doesn't get some features. So for example, it doesn't get the features for For example, this top feature is a straight line. In this case, it gives you a blob at the top. A two-dimensional space gives you a better representation. 3D gives you a very good representation. That's what is shown here. In this case, just to show, we are going to stick to 2D representation because I can plot it easily. It's the two-dimensional space of the coefficient of the latent space coefficients. Just those 2 points. So Z1 and Z2. So now we can plot all the ODFs in the database. So this is a database of 342,000 ODFs, very high dimensional space, completely shrunk down to 2 dimensions. Now I can plot every single point. Every point corresponds to a texture or ODF. I can color it based on properties. I can color it based on processes. In this case, it's colored based on elastic properties. So from a high elastic modulus to a low elastic modulus. You can see how it's spread out. It's already giving a structure in this space with lower elastic modulus coming here and the higher coming there. It can also give you a structure in terms of processes. So if you see the last process in the sequence, it gives you on outlier processes, which end up being rolling process. Once at the center end up being tension. So it gives you the structure that's split between different processes where you can interpolate across. Now, if you look at the generative part of this neural network, which is can you identify samples in this latent space, and from these samples generate textures that are not there in the database that you don't train with in the first place. So this is a predictive behavior of the variational autoencoder. That is things that are not in the database but that are predicted by simply sampling the latent space. So these are some points that I sample. If you see this endpoint, there are no points available there from the computations. They're still predicted. So if you take this point, that's this particular ODF that's being predicted. And if you take a point here, that's the ODF, and you can see it's very smooth. The transition from the left to the right, going across, starts from a texture with a feature on this side, 2 lines, and the lines get crushed towards the ellipse. So if you see 3 different points here, they get crushed towards the ellipse. There's also structure on this direction, so it starts from a line, goes to a line here, slowly transitions back to this. So it's a very cool way to synthesize these ODFs as a transition from one principal fiber component to another in the text, directly in the texture, but using a 2-dimensional space where someone can take a mouse, click on a point, identify, move it towards x-axis or y-axis, identify how the ODFs can change according to a process. So it's a good educational tool also if you're teaching courses in texture. Here is an example of what happens in a small point in this latent space. So if you just take a small, tiny point, you can get hundreds of ODFs because this is a very large database. You can try to plot all these points, and you can see variability within those regions. You can identify what kind of processes gives rise to a point in the latent space. And you can look at these processes. So the database generates all kinds of processes that leads to this point, with the outcome being, if you want a certain ODF, the answer is not unique. There are different processes that lead to the same ODF, but you can get it from the database. Not only that, you can use it as a generative means to identify new processes. Here is an example of process prediction. So we took certain sets of ODFs, which are not there in the database originally, to see what kind of processes that's being predicted. We know the process behind these ODFs, so we just want to see if they can be predicted. So what we do is we do proximity analysis. So we take these test sets, find what's the closest ODF in the database. You could also interpolate, find new ODFs, and then you can plot it as a function of the error from the input ODF. So the error starts to increase as you go farther and farther away in the latent space. But you can find ODFs that have very low errors, very close to the input ODF. Here is an example of one of the inputs. And these are 6 different ODFs that I get from the latent space. What you can see is some of them are very close to this, some of them are farther away. So if you see F, the error is very large, but also comes close in the latent space. So you can think of moving along the latent space to see these variability. And you can find out processes that correspond to this ODF and then find out if it matches what you gave as input. Same thing for another texture that I gave as input. A cool thing about this is you can identify much simpler processes. So this and the way I gave the input was a 4-step process. This was a 4-step deformation process that gave this. But from the database, we can identify much simpler processes. We can identify a 3-step process that can give you a similar ODF. So in a sense, reduce the complexity of your industrial forming process. So you get the same final property from a lower number of steps, or identify new processing routines that can save you money. Here is an example of finding ODFs with similar properties. We can also think of doing property optimization in this small latent space, 2-dimensional latent space, just by looking at points around this input ODF. Here we can identify completely new orientations that give you ODFs that give you the same property. So if you want 71 GPA as your elastic modulus, we can identify a completely new texture that gives you the 71 GPA modulus with a simpler process. That's what is interesting from the variational autoencoder perspective. So I come to future work. What can we do with this approach, variational autoencoder approach? There's been explosion of papers in this area, especially in microstructure field. There's been the papers are ramping up now because you can do certain cool things with autoencoders because it's a generative system. Can we directly work with microstructures? That's one of the questions. So can you take an image of a composite or a polycrystal, enough images to generate a latent space, and from which we can identify new failure modes, for example. So if you can have a failure mode that completely passes through or breaks down, using this, identify new failure modes and new processes or new microstructures that gives you different performance from the latent space. It also gives you a way to visualize variability of the microstructure. They're useful for uncertainty quantification. If you're interested in finding for a given process what's the variability in the properties, we can do it using a variational autoencoder because that's what it does. It gives you a probabilistic representation of the latent space. The new area that variational autoencoders are being used is for multiscaling and coarse graining. So if you think of molecular dynamics simulations or crystal plasticity simulations, you want to upscale it, you want to do a higher level simulation, you want to do coarse graining, or you want to do a macro scale simulation. Can you reduce the number of latent variables? Can you reduce the state variables in your simulation? So instead of using all your slip systems, reduce the slip systems to a certain number, a smaller set for a microstructure, so you can get the same outcome, stress strain curve, without going into a complete crystal plasticity model. So that there is interest in multi-scaling with variational autoencoders. Finally, the question is, this is something we are thinking about with the Air Force. We are recently working on this, identifying structure in the latent space, which means if you think of a simple example as you have animals and objects that we create, we can encode it with a encoder of infinite power. So there is something called encoder of infinite power, which will reduce everything to one dimension. We can have a deep neural network, highly nonlinear, that reduces any input to one-dimensional output. But is that useful? This is not probably useful because something like this may be more useful, where you have X and Y axis giving you different features of the same image. So for example, an animal which walks, or a car which goes on the ground versus something that flies is separated out from a feature that's living versus non-living. So this is a structure in the latent space, which we can create for microstructures also. We want to create the structure where we can separate functional attributes like properties, processes. We separate the microstructures based on those. So that's something of recent interest. Also identify what is the dimensionality. We don't know what's the dimensionality of these microstructure spaces. That's also of interest. I want to stop here. All the data from this talk is available on GitHub. There is a database with 342,000 microstructure ODFs that you can start to use if you are interested in this process design problem. We'll stop here.
Excellent talk, Professor Veera. Any questions? Please feel free to raise your hand or type in your questions in the chat box. Okay, I have one from Darshan. Yeah, Darshan, go ahead.
Good evening, sir. Can you listen to me?
Yeah, I can hear you.
It is a very good talk. I work a bit in textures, but I'm very new to data sciences and material informatics kind of thing. But my question can be, it might be a bit naive, but texture is only one particular property which generally is important when you're processing the material. So for example, when you say you go from random texture to some particular texture, you can have 2 to 3 different processing routes, but the different processing routes will generate different kinds of microstructures, different grain boundary properties, etc. So how is that kind of being, just looking at the texture, is it sufficient to comment on the uh, processing route itself?
Yeah, so texture is a, you're right. So texture is a lower dimensional descriptor, which is basically volume fraction information, right? You're looking at volume fractions of different orientations in the microstructure. And that primarily affects certain properties, and you have higher order variation. So I talked about Anand's work on 2-point correlations, which is much more higher dimensional, which tells you what's the correlation of uh, what's the probability of a grain next to another grain, this orientation next to another orientation, for example. You also have grain boundaries. It's a very tough problem. You have microstructure with grain boundaries, you have slip transmission, etc. So this is just a preliminary work on data science just for textures, but like I said, the goal really is to do full microstructure learning. So this is what we are going towards, which is directly working with EBST images.
Yeah, I got that
Directly
at the
working
end
with
of your presentation where you clearly mentioned
right,
that. But,
right.
yeah.
Yeah, so that's the future. And there are very few. There are basically no papers on this right now. So this is an open area of research. The issue with microstructures are there is no set size. So in a neural network, you want the input to be 200 by 200 image. But for microstructure, there's no set size. We don't know if it's a 200 by 200 or 100 by 100 EBST image. There is the issue with rotations of images. You can have a image that's rotated by 20 degrees that you need to classify. So you do augmentation techniques and data mining. A rotated image of a cat versus a straight image. So there are issues with images. There are no issues with textures because textures, I know exactly what's the dimensionality. There's no
But
question whether it's 100 by 100, etc.
within the textures itself, also, like sometimes the texture evolution is sluggish due to some particular processing, but sometimes the rate of texture evolution is quicker compared to some other processes. So
Right.
uh, means again the processing again kind of comes into the picture over here. What processing
Yeah,
technique
so
you're doing?
that is correct. So that's why we use the process model. So we need to have the way the process model is generated, it uses this crystal plasticity approach, which takes care of the slip system resistances. So if some slip systems may be hard that you cannot deform, a system may not twin under tension, but twin under compression for HCB material. So you can put all that information in your computational model.
Okay, thank you.
Okay. Any other questions? Okay, if not, may I ask you 2 small questions?
Yeah, go ahead.
First, why starting with the initial random texture? Is there a particular reason for that?
Yeah, so typically processes start from a cast texture, which is random. So we start with the random texture. So that's the initial bulk material. Typically you get in industry, fully cast structure, and then you start to deform it. So we want to always start from a random initial input, but that's not a restriction for our database because you can always start from, we have enough microstructures here that you can go and start. If you think of this, you can always start from this tension texture and then you can go because it's already existing in the database. Yeah.
Okay. So what is the size of your initial ODF that you're putting in?
The initial ODF, I had a picture here. So this was, so ODF, you can make a mesh with different number of nodes. So we started with a 145 node structure. So we had 76 independent nodes, which you use for the training. But you can think of using a more refined ODF, which is 399 nodes. It just increases the complexity of your neural network.
But will this change if you're starting from a random texture to, let's say, a more concentrated texture, right? If after a certain amount of deformation, you have more cube texture or S texture, then you have to refine your ODFs locally. or at least
Right.
sampling points in the ODF locally. How will that work?
So the good thing about this nodal representation is we can have very fine textures, because I can have a node with, unlike Fourier, if you do Fourier transforms, you cannot get this sharp textures unless you have lots of coefficients. But in the finite element space, you can actually do very fine textures, because I can have a node with very high intensity with a single crystal, basically, if you have only one node with a delta function. That can be done, but to answer your question in a more refined way, you can always start with a very fine discretization. So that will, you assume that it captures sharp textures that you can get from certain processes. Or
So
single
there's
crystal.
adaptive meshing, as in when you go with deforming. So
Right.
the mesh is static.
Either adaptive meshing, or you can start from scratch with a very fine discretization.
Okay.
It can help you.
And just a blatant plugin. So you had a last slide which says what is the optimal dimensionality of the microstructures. In fact, we were and we are looking at essentially the same problem, except that we call it as intrinsic dimensionality. We just published something along those lines in IMMI journal. In fact, we didn't go to the textures, but we just took a two-phase composite material, both in 2D and 3D, looking at different volume fractions and saw what is the intrinsic dimensionality of the problem of precisely the space using PCA and two-point correlations. And the results are interesting. I mean, please have a look if you have time. That would be
right. Yeah. So we are trying to go to this variational autoencoders to see if further reduction can be achieved. The other issue is PCA is a subset of a variational autoencoder. So you can think of a more complex PCA analysis. So I'll look at your paper, and so we can maybe use your database with variational autoencoders. So it could be a collaboration.
sure.
I can take your data and use a VAE to see if I get the same dimensionality. It'll be cool.
Definitely, that would be a good thing. And I think there's one person, George from Airbus, wants to ask a question. George, if you can hear me, please go ahead and ask. George? Okay, looks like he has left. Okay, looks like, just give me a second. Okay, I have unmuted you, George.
Hello.
I can hear you.
Yeah. Good morning, sir. Very insightful. I'm new to this data analytics and ML and AI, but my question is like we are trying to develop a ALM process for wire feed DED for TI-64, and as we have this sharp texture in the Z direction, we want to, our final objective is to get the optimal or equiaxed grain structure. In that case, how do we this kind of machine learning will help us to reduce the number of tests and to get this EBST data into the data file? Can you give some insight there, sir? How do we go about? Because today we are doing lots of tests, physical tests, and trying to find out the microstructure and find out the property correlation. But if you can some light on that, sir.
Yeah. So I mean, all machine learning techniques depend on a database. So if you have enough experiments, you probably already have data sets to do correlations. So if you have a database of EBST images, and you know for every EBST image what's the process, then we could develop a data mining approach or a simple neural network that can take from EBST. So think of a variational autoencoder like this. I mean, an encoder like this that takes in your EBST images, and then the output, if you take just the first output, could be your process. So we can develop something like this. In a more general sense, the way we think of material science, data sciences, is that computational data is more prevalent than experimental data. Typically, you have very small amount of experimental data, very large amount of computational data. So the whole goal of materials informatics, it's different from what Google does with its images, is to do transfer learning. That is, you train your network for a wire EDM process. For example, you develop a computational model first, a crystal plasticity model. You develop a neural network where you can get these coefficients of your weights of your neural network, and then do a what is called a transfer learning, which forks the network. You add one more layer, just add a layer at the end, retrain that layer to predict your experiments. The idea is the computational simulation has a structure in the sense that's transferable to experiments, but it doesn't have the full information. So we use that in addition to your experiments to develop a model. So that's called transfer learning. That's becoming very popular now. So I would suggest using some of those techniques for your case. But for a start, if you want to understand how do you go from eBSD to your process, you can think of starting with a neural network directly with your images, eBSD images.
Okay, sir. Yeah, that's great insight. And what is the data set is required some minimum to start with on the eBSD?
So you can work with images directly. There are Python scripts, or if you use MATLAB, there are MATLAB things like Google Net. You can use current deep learning networks that are already available, like Google Net. The input is image. You need to give an image. The image dimension is 224 by 224. So if you can take your eBSD, make 224 pixels by 224, you can already start training using existing networks.
But to have a robust model, sir, what is the number of images is required, or more number of images is better model, sir? Or what do you?
Yeah, more number of images better. So I would start with a few hundred. Okay. Few hundred should be enough to generate a very basic database, and then you can train from there.
Yeah, thanks a lot, sir. Yeah, thank you so much.
Any other questions? Okay, if not, we thank the speaker. Thank you very much for a very good talk.
Thanks, Anand.
Thanks. So I'll stop the recording.